Tonight, we descend beneath the surface of reality itself. Beneath atoms, beneath protons and neutrons, beneath everything solid you have ever touched. We are traveling into the hidden world of quarks, tiny entities that build the visible universe. And yet, strangely, no one has ever seen a single quark alone. Not once. Not anywhere in the cosmos. The universe refuses to allow it. If you watched our earlier journey into neutron stars here on Velarin, Sleepy Space Mysteries, you may remember how matter collapses into forms almost impossible to imagine. Tonight's mystery begins even deeper than that. Far below stars, far below atoms, down where reality itself starts to blur. Before we begin, take a quiet moment to subscribe, leave a like, turn on notifications, and perhaps join the channel membership if you enjoy these long cosmic explorations. And tell me softly in the comments, where in the world are you listening from tonight? Now settle in comfortably, let the lights dim, and let your thoughts drift downward into the smallest architecture of existence. For thousands of years, humanity believed atoms were the final layer of matter. Tiny, indivisible pieces that could never be broken apart. But science kept digging deeper. First came electrons, then nuclei, then protons and neutrons, and finally, physicists uncovered something even stranger hiding inside them all. Quarks, tiny particles carrying bizarre fractional charges. Particles bound together by the strongest force in nature. A force so unusual that it becomes stronger when you try to separate its objects. Like a cosmic trap tightening its grip. And if you pull too hard, reality responds in an astonishing way. The universe creates entirely new matter from pure energy rather than allow a quark to escape alone. Tonight, we will slowly uncover why. For most of human history, the idea of matter seemed simple. Stones were solid, water flowed, fire burned. Air moved invisibly around the world. People experienced matter directly through touch and sight, but nobody knew what matter truly was beneath the surface. The universe appeared continuous and smooth. A mountain looked solid. A river looked unbroken. Even the night sky seemed like a seamless ocean of stars stretching forever overhead. Then, more than 2,000 years ago, a Greek philosopher named Democritus imagined something astonishing. He proposed that all matter might be built from tiny indivisible units. He called them atomos, meaning uncuttable. His idea was radical because it suggested that everything in existence, from oceans to human bodies, could be reduced to unimaginably small particles moving through empty space. But Democritus had no microscopes, no experiments, no particle accelerators, only thought itself. And for centuries, his idea remained philosophy rather than science. Humanity continued living among matter without understanding its hidden architecture. Kingdoms rose and vanished. Entire civilizations flourished beneath skies whose true structure remained invisible. Meanwhile, atoms waited silently beyond the limits of human perception. By the 19th century, science finally began uncovering evidence that matter truly was atomic. Chemists noticed that elements always combined in fixed ratios. Water always formed from the same precise balance of hydrogen and oxygen. Carbon dioxide always emerged from the same proportions of carbon and oxygen. The consistency was too perfect to be accidental. John Dalton realized these patterns made sense if matter consisted of discrete particles combining like tiny building blocks. Atoms were no longer philosophical speculation. They became scientific reality. And yet, even then, scientists believed atoms were fundamental. Tiny eternal spheres forming the final layer of existence. That belief shattered in 1897. A physicist named J. Thomson discovered the electron. Tiny negatively charged particles emerging from inside atoms themselves. Suddenly, atoms were no longer indivisible. They contained smaller structures hidden within. It was the first great descent into matter. Soon after, Ernest Rutherford performed his famous gold foil experiment. He fired energetic particles at thin sheets of gold and expected them to pass gently through. Most did, but some bounced backward violently, as if they had struck something impossibly dense hidden inside the atom. Rutherford realized the atom was mostly empty space. At its center sat a tiny nucleus containing nearly all the atom's mass. If an atom were expanded to the size of a giant cathedral, the nucleus would be smaller than a grain of dust suspended at the center. Everything else would be emptiness. This realization remains deeply unsettling even today. The chair beneath you, the walls around you, your own body, nearly all of it is empty space held together by invisible forces. The nucleus itself contained protons and neutrons. Electrons drifted around them in strange quantum clouds. By the early 20th century, scientists believed they had finally reached the bottom layer of reality. 3 particles seemed sufficient to explain all matter in the universe. But nature was not finished surprising us. When physicists began smashing protons together at high energies, the results became strange. Truly fundamental particles should behave like solid, indivisible points. Instead, protons behaved as though smaller objects rattled around inside them. The deeper scientists looked, the stranger the proton became. In the 1960s, experiments at the Stanford Linear Accelerator Center fired electrons into protons with incredible energy. The scattering patterns revealed hard internal structures hidden within the proton. Something smaller lived inside. At the same time, particle accelerators were discovering an overwhelming zoo of mysterious particles. Kaons, pions, lambdas, sigmas. Hundreds of exotic entities appeared briefly during violent collisions and then vanished again. Physics seemed to be drowning in complexity. Then came a beautiful idea. 2 physicists, Murray Gell-Mann and George Zweig, independently proposed that all these particles might be combinations of even smaller ingredients. Tiny entities with fractional electric charges. Tiny building blocks forming a hidden alphabet beneath matter itself. Gell-Mann gave them a strange name borrowed from literature. Quarks. At first, the idea sounded absurd. Every known particle carried whole number electric charges. Electrons carried -1. Protons carried +1. But quarks carried bizarre fractions. An up quark possessed a charge of +2/3. A down quark carried -1/3. And yet, somehow, the mathematics worked perfectly. 2 up quarks and 1 down quark combined into a proton with total charge +1. 1 up quark and 2 down quarks formed a neutron with charge 0. Suddenly, the hidden structure of matter became visible. Protons were not fundamental. Neutrons were not fundamental. Beneath them lived quarks. tiny restless entities moving inside the atomic nucleus like imprisoned sparks. But another mystery immediately emerged. Every attempt to isolate a quark failed. No matter how violently physicists smashed particles together, no lone quark ever appeared. It was as though the universe itself refused to let quarks exist alone. And the reason for that refusal would lead physicists toward one of the strangest forces ever discovered in nature. At first glance, quarks seem almost impossible to understand. They are unimaginably small, smaller than anything humanity has ever directly observed. Even the proton, which itself is already tiny beyond comprehension, is vastly larger than the quarks moving inside it. Modern experiments suggest quarks may have no measurable size at all. They behave as point-like particles with no internal structure. Tiny mathematical points carrying energy, charge, spin, and something even stranger, color charge. Now the word color is deeply misleading. Quarks are not literally red or blue or green. They do not glow with color like lights in the darkness. The names are simply labels physicists invented to describe a peculiar property of the strong nuclear force. They could have called them Type 1, Type 2, and Type 3. But the color analogy proved surprisingly useful because different colors combine into neutrality much the same way visible colors combine into white light. Every quark carries one of three color charges: red, green, or blue. And nature imposes a strict rule upon them. Observable particles must always be color neutral. This means quarks cannot arrange themselves randomly. A proton contains three quarks whose colors combine into neutrality. One red, one green, one blue. Together they form a stable colorless state. Mesons, another family of particles, contain one quark paired with one antiquark carrying opposite color charges that cancel perfectly. This hidden balancing act governs the structure of matter itself. But why should color neutrality matter so much? Why can quarks not simply drift freely through space carrying color charge openly? To answer that, we must descend into the strange force binding quarks together. A force unlike anything in ordinary life. Physics recognizes four fundamental forces shaping the universe. Gravity governs planets, stars, and galaxies. Electromagnetism governs light, chemistry, electricity, and the structure of atoms. The weak nuclear force allows radioactive decay and powers reactions inside stars. And then there is the strong nuclear force, the strongest force in existence. It is so powerful that it overcomes the electromagnetic repulsion between positively charged protons packed together inside atomic nuclei. Without it, every atom in the universe would instantly fly apart. This force is carried by particles called gluons. The name itself sounds almost playful, as though these particles simply glue quarks together. But the reality is far stranger and far more beautiful than that simple description suggests. Photons, which carry electromagnetism, are electrically neutral. They transmit force without participating in it themselves. Two beams of light can pass directly through one another without interaction. Gluons behave differently. Gluons themselves carry color charge. This single fact changes everything. Because gluons carry the very charge associated with the force they transmit, they can interact with each other endlessly. They pull on one another, twist around one another, create dynamic storms of interaction between quarks. The force field inside a proton becomes an intensely active sea of gluon exchanges constantly fluctuating and rearranging itself. And from this strange behavior emerges one of the most shocking properties in all of physics. The strong force grows stronger with distance. This completely violates human intuition. Gravity weakens as objects move apart. Electromagnetism weakens with distance too. A magnet becomes weaker the farther away you hold it. Light fades as it travels across space. Nearly every force humans experience becomes weaker with separation. But the strong force behaves in reverse. When quarks sit very close together, they interact only weakly. Physicists call this asymptotic freedom. Inside a proton, quarks move around with surprising independence because at extremely tiny distances the strong force relaxes its grip. But if you try pulling quarks apart, the force does not weaken. It tightens. Imagine stretching a rubber band that becomes harder and harder to pull the farther it extends. No matter how much strength you use, resistance increases relentlessly. Between separating quarks forms something called a flux tube, a narrow filament of gluon energy connecting them together. Unlike electric fields, which spread outward through space, this gluon field compresses itself into a concentrated tube. As the quarks separate, the tube stretches longer, and the energy inside it rises continuously. The farther apart the quarks move, the more energy the flux tube contains. Pulling them apart requires enormous energy, then even more energy, then vastly more. Eventually, the energy density becomes so immense that reality itself responds. And this is where the universe reveals its deepest trick. Instead of allowing the quarks to separate freely, the energy inside the flux tube transforms into entirely new particles. A new quark and antiquark pair suddenly emerge from the vacuum itself. Matter created from pure energy. The original flux tube snaps, but not into two isolated quarks. Instead, the newly created particles immediately bind with the originals, forming entirely new composite particles. No lone quark ever appears. The universe would rather manufacture new matter than permit quark isolation. This phenomenon is called confinement. And confinement is not merely difficult to overcome. It appears fundamentally absolute. Every experiment humanity has ever performed supports this strange rule. Particle accelerators smash protons together at nearly the speed of light. Tremendous energies blast quarks apart momentarily. Yet detectors never observe free quarks emerging independently. Instead, they see sprays of ordinary particles called jets, cascades of newly formed hadrons appearing as quarks become trapped again almost instantly. The quarks are always hidden, always confined, always imprisoned together by the strongest force in nature. And strangely, this imprisonment may be the very reason matter itself can exist at all. The deeper physicists explored confinement, the stranger the universe appeared to become. At first, many scientists suspected free quarks simply had not yet been detected because technology remained too limited. That assumption seemed reasonable. Human instruments had once failed to see atoms. Later they failed to see nuclei, then electrons. History repeatedly showed that hidden layers of nature eventually revealed themselves as technology improved. But quarks resisted every attempt at liberation. Physicists searched for particles carrying fractional electric charges. A lone-up quark would possess a charge of positive 2/3. A lone-down quark would carry negative 1/3. Such charges would stand out immediately because nearly every known particle carries whole number multiples of electric charge. Experiments searched everywhere. They searched inside cosmic rays arriving from violent regions of deep space. Some cosmic rays contain energies millions of times greater than those produced inside the Large Hadron Collider. If extreme energy could free quarks, the heavens themselves should occasionally produce them naturally. Nothing appeared. Researchers searched in underground laboratories shielded from background radiation. They examined lunar rocks brought back by Apollo astronauts. They studied ocean water, meteorites, and ancient minerals. They built exquisitely sensitive detectors capable of identifying even tiny traces of fractional charge. Again, nothing. The universe remained stubbornly silent. And gradually physicists realized something profound. Confinement was not a temporary mystery waiting for better machines. It was woven directly into the mathematics of reality itself. Quantum chromodynamics, the theory describing quarks and gluons, predicts confinement naturally. The equations themselves imply that isolated color charge cannot survive at large distances. The vacuum of space resists it. This idea feels strange because human intuition imagines empty space as passive emptiness, a silent void where particles simply drift. But modern physics paints a very different picture. The vacuum is alive. Even in perfect emptiness, quantum fields fluctuate constantly. Virtual particles flicker briefly into existence and disappear again. Tiny storms of energy ripple through space at every moment. The vacuum is not dead emptiness. It is restless activity hidden beneath stillness. Inside this restless quantum sea, gluons interact with one another endlessly. Their self-interactions create the confinement mechanism that traps quarks forever inside composite particles called hadrons. And because confinement dominates ordinary matter completely, humans never directly experience quarks themselves. We only experience the larger structures built from them. A proton, for example, is not merely three tiny quarks sitting quietly together. It is a violently dynamic system. Quarks race near the speed of light inside it. Gluons continuously appear and vanish. Additional virtual quark pairs emerge briefly from the vacuum before annihilating again. The interior of a proton resembles a chaotic storm far more than a tiny solid sphere. And yet, despite this internal chaos, the proton remains astonishingly stable. In fact, protons may survive for periods longer than the age of the universe itself. Think about that quietly for a moment. Inside every atom of your body are protons that may outlive stars, galaxies, perhaps even most structures the cosmos will ever produce. Tiny confined storms persisting through unimaginable stretches of time. But another mystery waited hidden within protons. When scientists calculated the masses of individual quarks, something shocking emerged. Up and down quarks are incredibly light. Their combined masses account for only a tiny fraction of the proton's total mass. So where does the rest come from? The answer is extraordinary. Most of the proton's mass does not come from quarks themselves. It comes from energy. Specifically, the immense kinetic energy of quark motion and the energy stored inside gluon fields. Einstein's famous relationship between energy and mass means this restless internal activity creates the majority of the proton's weight. And because protons make up nearly all visible matter, this means most of the mass in your body comes not from particles themselves, but from confined energy trapped inside quark systems. The chair beneath you, mountains, oceans, trees, human bones. Almost all visible mass in the universe emerges from confined gluon energy. Matter is not as solid or simple as it appears. At the deepest level, reality resembles organized vibrations of energy bound together through invisible fields. This realization slowly transformed humanity's understanding of existence itself. The ancient dream of indivisible atoms dissolved completely. Matter was no longer tiny billiard balls. Instead, particles became excitations of underlying quantum fields. Quarks emerged from quark fields, electrons from electron fields, photons from electromagnetic fields. The universe became less like a machine and more like a cosmic symphony of interacting vibrations. And among those vibrations, quarks remained uniquely imprisoned. Even gluons cannot escape confinement. Because gluons carry color charge themselves, they too become trapped inside hadrons. No isolated gluon has ever been observed independently. The carriers of the strong force are imprisoned by their own interactions. There is something strangely poetic about that. The force that binds matter together also traps its own messengers forever. And yet confinement itself may not operate identically under all conditions. Physicists discovered that at unimaginably high temperatures and pressures, matter changes into something exotic called quark-gluon plasma. Inside this state, quarks and gluons move more freely across short distances, no longer confined inside individual protons and neutrons. For a brief moment, the universe returns to a condition resembling its earliest beginnings. Moments after the Big Bang, the cosmos was so hot that ordinary matter could not exist. Temperatures exceeded trillions of degrees. Protons and neutrons had not yet formed. Instead, the young universe contained a dense ocean of quarks and gluons flowing together in a searing plasma. The entire observable universe once existed in this strange state. Only as the cosmos expanded and cooled did confinement gradually lock quarks into stable particles. Protons formed, neutrons formed. Eventually atoms emerged, then stars, galaxies, planets, oceans, life. Everything familiar arose because confinement froze the chaos of the early universe into stable structures. Without confinement, atoms could never exist. Chemistry would vanish. Stars would never ignite. Human beings would never awaken beneath the night sky wondering what matter truly is. The imprisonment of quarks may seem cruel from a human perspective. But without that imprisonment, the visible universe itself would disappear. And still, one haunting mystery remains. Why does nature enforce confinement so absolutely? Why should the laws of reality care whether color charge remains hidden? Why should the universe forbid free quarks so completely? Even today, despite decades of progress, physicists do not possess a fully rigorous mathematical proof explaining confinement from first principles. We know it happens. We observe its consequences constantly. But the deepest reason may still be waiting silently beneath the surface of physics itself. There is something deeply unsettling about confinement when you stop and think about it long enough. The universe allows us to infer quarks. We can calculate their properties. We can map their behavior with astonishing precision. We can observe the trails they leave behind inside particle detectors. And yet the quarks themselves remain permanently hidden behind a veil of confinement that no experiment has ever pierced. It is almost as though nature deliberately reveals only shadows. Imagine trying to understand an ocean while never seeing water directly. You only observe waves striking the shore. You measure tides. You watch storms crossing the horizon. Piece by piece, you infer the existence of the sea itself without ever touching its depths. That is humanity's relationship with quarks. We know they are real because the mathematics describing them predicts reality with breathtaking accuracy. Quantum chromodynamics has survived every experimental test physicists have devised. The collisions inside particle accelerators match its predictions almost perfectly. Jets of hadrons emerge exactly where quarks and gluons should have traveled. The masses of particles align with calculations derived from quark interactions. The structure of atomic nuclei depends entirely upon confinement behaving precisely as theory predicts. And still, the quarks remain inaccessible. The more powerfully we probe matter, the more violently confinement responds. This creates a strange philosophical tension inside modern physics. Science traditionally advances by isolating objects and studying them independently. We isolate atoms, trap electrons, separate molecules, but quarks refuse isolation completely. Their very identity depends upon relationship and interaction. A lone quark may not merely be difficult to produce. It may be meaningless. Some physicists suspect confinement hints at something profound about reality itself. Perhaps the universe is not fundamentally built from isolated objects at all. Perhaps relationships are more primary than the particles participating in them. Inside a proton, quarks cannot be understood independently from the gluon field binding them together. Their identities blur into the larger system. The proton behaves not like three separate particles tied loosely together, but like a unified quantum entity whose internal boundaries constantly shift and dissolve. The deeper physics descends, the less reality resembles ordinary objects. This strange interconnectedness becomes even more mysterious when viewed through the lens of quantum mechanics. Quantum particles do not behave like tiny classical balls hidden inside matter. They exist as probability waves. They fluctuate between possibilities until interactions force measurable outcomes. Quarks inside hadrons occupy a constantly shifting sea of quantum uncertainty. At any instant, the proton contains not only its three primary quarks, but also countless virtual gluons and temporary quark pairs emerging from the vacuum itself. The proton becomes less like a stable object and more like a dynamic storm of probabilities. And yet this storm creates stability. That paradox lies at the heart of modern physics. Chaos produces order. Invisible fluctuations produce solid matter. Confined energy produces the mass of worlds. When you touch a stone, you are touching organized quantum fields held together by confinement mechanisms born in the first moments after the Big Bang. Even more strangely, the proton itself may not be eternal after all. Some grand unified theories predict that protons could eventually decay over unimaginable spans of time. Experiments deep underground have searched for signs of proton decay for decades. Vast detectors buried beneath mountains wait silently inside darkness, monitoring enormous tanks of water for the faint flashes that would signal a proton dissolving into lighter particles. So far, nothing has appeared. If proton decay happens, it occurs incredibly slowly. Current evidence suggests the proton's lifetime exceeds at least 10 raised to the 34 years. That number is so enormous it barely fits inside human thought. It is vastly longer than the current age of the universe. And still, physicists continue watching. Because beneath every answer, new mysteries emerge. That pattern repeats endlessly throughout science. Atoms once seemed fundamental. Then came nuclei. Then protons and neutrons. Then quarks. Now physicists wonder whether quarks themselves may hide deeper layers still undiscovered. So far, every experiment suggests quarks are truly fundamental. They behave as perfect point particles with no measurable size. But history teaches caution. Humanity has repeatedly mistaken temporary boundaries for final truth. Perhaps future civilizations with technologies beyond our imagination will descend even deeper into matter. Perhaps quarks themselves are woven from structures hidden beneath current physics. Tiny strings, quantum geometries, vibrations inside higher dimensions, or something stranger still beyond language entirely. We do not know, and that uncertainty is beautiful, because it means the universe remains alive with mystery. Even now, beneath every atom around you, quarks move invisibly within their confinement. Tiny storms of color charge flicker silently inside the matter of your body. Ancient particles forged from the cooling fire of the early cosmos continue their endless quantum dance beneath your skin at this very moment. You never feel them directly. You never see them. Yet without them, you would not exist. The stars would not shine. Planets would never form. Chemistry would collapse into silence. Confinement may appear at first like a prison imposed upon quarks, but perhaps it is better understood as a creative force, a cosmic sculptor shaping chaos into stable matter, a hidden law transforming the violent energy of the young universe into galaxies, oceans, forests, and conscious minds capable of wondering where they came from. And somewhere inside that vast chain of transformations sits one impossible truth. The universe would rather create new matter from pure energy than allow a quark to stand alone. Even now, physicists continue smashing particles together beneath the border of France and Switzerland. Deep underground tunnels hum with magnetic fields guiding protons near the speed of light. Detectors larger than cathedrals wait patiently for tiny collisions lasting less than a trillionth of a second. Humanity keeps searching, keeps descending, keeps asking whether the bottom layer of reality has finally been reached. But perhaps the greatest lesson quarks offer is not about particles at all. Perhaps it is this: the deeper we travel into the universe, the less isolated everything becomes. Matter depends upon forces. Forces depend upon fields. Fields fluctuate together inside a shared quantum fabric stretching across the entire cosmos. And somewhere within that hidden fabric, beneath stars and galaxies and sleeping worlds, quarks remain forever bound together in darkness, quietly holding reality itself intact. Long before humanity existed, long before Earth formed from dust around the young sun, the universe itself passed through a phase where quarks briefly moved freely across space. To understand confinement completely, we must travel backward almost 14 billion years to the beginning of cosmic history itself. back to a time before atoms, before stars, before light could travel unhindered through the cosmos. Back to the first fractions of a second after the Big Bang, when the entire observable universe was smaller than a grain of sand and hotter than anything the human mind can comfortably imagine. In those first moments, temperature dominated everything. The newborn universe was not made of matter in the ordinary sense. There were no atoms, no nuclei, no protons or neutrons. Even the concept of stable particles barely applied. Temperatures exceeded trillions upon trillions of degrees. Energy flooded every region of space with unimaginable intensity. Under such conditions, confinement could not operate normally. Quarks and gluons existed inside a seething ocean called quark-gluon plasma. This plasma was unlike any material humans encounter in ordinary life. It was not solid, liquid, or gas. It was a dense fluid of liberated quarks and gluons moving almost freely through one another. Color charges still interacted violently, but stable hadrons had not yet formed. The universe was too hot for confinement to lock quarks into permanent structures. For a brief cosmic instant, nature existed without protons or neutrons. And yet, even during this primordial freedom, the seeds of future structure already existed hidden within the laws of quantum chromodynamics. As expansion cooled the universe, confinement slowly emerged. Temperatures dropped below a critical threshold. The strong force changed behavior. Quarks became trapped together inside newly forming hadrons. This event transformed cosmic history forever. Without confinement, the universe would have remained a chaotic sea of plasma. Stable matter could never have formed. But as quarks locked themselves into protons and neutrons, the foundation for everything familiar appeared. Within minutes, atomic nuclei began forming. Hundreds of thousands of years later, electrons joined those nuclei to create atoms. Then gravity gathered matter into stars and galaxies. Heavy elements formed inside stellar furnaces. Eventually planets emerged. Oceans formed. Life awakened. Every human story began with confinement cooling the early universe into stable matter. And strangely, modern physicists can briefly recreate those ancient conditions. At facilities like the Large Hadron Collider in Europe and the Relativistic Heavy Ion Collider in America, scientists smash heavy atomic nuclei together at extraordinary speeds. Gold nuclei, lead nuclei. Entire atomic cores accelerated until they move at nearly the speed of light. When these collisions occur, temperatures briefly rise above those of the early universe itself. For a tiny fraction of a second, confinement melts. A droplet of quark-gluon plasma appears. Inside this microscopic fireball, quarks and gluons move with far greater freedom than they normally possess inside hadrons. The plasma behaves almost like a perfect liquid with astonishingly low viscosity. It flows with eerie smoothness, more smoothly than water, more smoothly than any ordinary substance ever measured. The universe briefly remembers its own beginning. Then the plasma cools almost instantly. Confinement returns. Quarks become trapped once again inside jets of newly formed particles racing outward from the collision point. These experiments revealed something unexpected. Quark-gluon plasma does not behave like a weak gas of independent particles as many physicists originally predicted. Instead, it behaves as an intensely interacting fluid. Even in their temporary freedom, quarks remain deeply connected through gluon interactions. The universe never entirely releases its grip. And this raises profound questions about the nature of freedom itself at the quantum level. Even when confinement weakens under extreme conditions, complete independence may still remain impossible. Some neutron stars may contain similar exotic states hidden deep within their cores. These collapsed stellar remnants pack masses greater than the Sun into spheres only a few kilometers wide. Pressure inside them becomes so extreme that atomic nuclei themselves may dissolve. Protons and neutrons may partially melt into dense quark matter hidden beneath the crust. If this is true, then scattered across the galaxy may exist enormous natural reservoirs of partially liberated quark matter silently rotating through darkness. Strange stars, quark stars, objects balancing between confinement and freedom. Physicists are still uncertain whether such stars truly exist, but observations continue hinting at strange possibilities. Some neutron stars appear smaller or denser than standard models predict. Others cool in unusual ways, suggesting unfamiliar internal structures. Deep inside these collapsed remnants, matter may exist in forms unlike anything found naturally elsewhere in the modern universe. And perhaps even stranger possibilities remain hidden. Some theories suggest stable clumps of exotic quark matter called strangelets could exist. These hypothetical objects would contain up, down, and strange quarks bound together into unusually stable configurations. Unlike ordinary nuclei, strangelets might possess bizarre properties, allowing them to survive outside normal atomic structures. So far, no confirmed strangelet has ever been observed. But the possibility remains fascinating because it reminds us how incomplete our understanding still is. Even after decades of studying quarks, the strong force continues hiding surprises inside its mathematics. One reason confinement remains difficult to understand completely is that quantum chromodynamics becomes mathematically brutal at large distances. At short distances, where quarks interact weakly, physicists can calculate predictions with elegant precision. But as confinement strengthens, the equations become overwhelmingly complicated. The gluons interact with each other endlessly. Quantum fluctuations multiply. Infinite possibilities overlap inside the calculations. Standard mathematical techniques begin failing. To study confinement properly, physicists often rely on giant supercomputers running lattice QCD simulations. In these simulations, spacetime itself becomes a vast numerical grid. Quarks and gluons interact across discrete points while computers calculate billions upon billions of possible interactions. Some of the world's most powerful computers spend years modeling these invisible quantum storms. And slowly, piece by piece, the simulations confirm what experiments reveal. Confinement is real, relentless, universal. The farther quarks separate, the stronger the force binding them becomes. Nature appears designed to prevent isolation at the deepest level of matter itself. And perhaps somewhere inside that strange rule lies a hidden principle humanity has not yet fully understood. Because again and again, the universe seems to whisper the same unsettling truth. Nothing fundamental exists entirely alone. One of the strangest aspects of quarks is that they force humanity to rethink what it even means for something to be real. In ordinary life, reality feels straightforward. A stone exists independently whether anyone observes it or not. A tree stands quietly in a forest. A planet circles its star through silent darkness. Human intuition assumes objects possess stable identities independent from relationships. But quarks challenge that assumption at the deepest level. A quark can never appear as an isolated object. Its existence is inseparable from the gluon fields and partner quarks surrounding it. Remove those relationships and the quark does not simply escape. Instead, the entire system reorganizes itself to prevent isolation from occurring at all. Reality protects connection. This strange principle becomes even more mysterious when viewed through the mathematics of symmetry. Modern physics is built upon symmetries hidden beneath nature. Symmetries determine conservation laws. They shape interactions. They govern the behavior of particles across the universe. Color charge itself emerges from a deep mathematical symmetry called SU3 gauge symmetry. Beneath the equations of quantum chromodynamics lies an elegant geometric structure describing how quarks and gluons transform into one another through color interactions. To physicists, these symmetries feel almost uncanny. Nature seems written in mathematics long before conscious minds evolved to discover it. Equations invented on chalkboards somehow predict invisible particles later confirmed by giant machines buried underground. Abstract geometry reaches across billions of years to describe the hidden structure of matter itself. And confinement emerges naturally from that geometry. It is not added artificially. It arises from the self-interacting nature of gluons and the symmetry governing color charge. The equations themselves seem to forbid isolated quarks. Some physicists find this deeply beautiful. Others find it unsettling, because it suggests the universe may not merely obey mathematics. It may fundamentally be mathematics. This idea becomes even more fascinating when we consider vacuum energy. Empty space appears simple to human senses, but quantum field theory reveals that the vacuum contains immense hidden complexity. Virtual particles constantly emerge and vanish. Fields fluctuate endlessly. Even perfect emptiness possesses measurable energy. Inside quantum chromodynamics, the vacuum itself behaves almost like a medium influencing confinement. Color fields distort the vacuum around them. Flux tubes emerge from interactions between quarks and the structure of spacetime itself. The vacuum becomes an active participant in binding matter together. In a sense, every proton around you continuously interacts with the fabric of empty space. And this interaction creates stability. The implications become astonishing when extended across the cosmos. Every atom in every star depends upon confinement operating identically everywhere in the observable universe. Whether inside distant galaxies billions of light-years away or inside your own bloodstream, quarks obey the same invisible laws with extraordinary precision. The strong force appears universal, timeless, unchanging. If its strength differed even slightly, the universe would look completely different. A weaker strong force might prevent stable nuclei from forming. Hydrogen could exist, but heavier elements might never emerge inside stars. Carbon chemistry would vanish. Life as humans know it would become impossible. If the strong force were slightly stronger, nuclear reactions inside stars would proceed differently. Stellar lifetimes might shorten dramatically. The balance between matter and energy across the cosmos would shift. Reality exists within an extraordinarily delicate range of physical laws, and confinement sits directly at the center of that balance. This realization has led some physicists toward the anthropic principle. The idea suggests the universe appears finely tuned for complexity because only such a universe could produce observers capable of asking these questions. If physical laws differed radically, conscious life might never emerge to notice. Other physicists dislike this reasoning intensely because it feels philosophically incomplete. They continue searching for deeper explanations, hidden beneath the apparent tuning of nature. Perhaps one day a more fundamental theory will reveal why the constants of physics possess their exact values. Perhaps confinement itself emerges from an even deeper layer of structure beneath quantum chromodynamics. String theory attempts one possible path toward that deeper layer. In some versions of string theory, particles are not point-like objects at all. Instead, they are tiny vibrating strings existing within higher-dimensional spacetime. Different vibrations produce different particles. Quarks become specific modes of string vibration interacting through hidden geometries curled beneath observable reality. Interestingly, string theory naturally produces structures resembling flux tubes. Some physicists discovered deep mathematical connections between quark confinement and higher-dimensional gravitational theories. Through ideas like holographic duality, calculations describing black holes in higher dimensions can sometimes model strongly interacting quark systems. The universe begins to feel almost dreamlike at this level. Black holes relate mathematically to quark plasmas. Geometry transforms into particle interactions. Space and information intertwine through hidden correspondences that no human would have imagined only a century ago. And yet experiments continue confirming these strange theoretical insights again and again. The deeper science travels, the stranger reality becomes. Still, despite all this complexity, quarks quietly shape ordinary life in ways humans rarely notice. Every heartbeat depends upon atoms forged from confined quarks inside ancient stars. Every breath contains nuclei stabilized by the strong force. The calcium inside bones, the iron inside blood, the oxygen moving through lungs. All of it exists because confinement transformed the chaos of the early universe into stable matter billions of years ago. There is something peaceful about realizing this. The same force binding quarks inside protons also indirectly holds together mountains, forests, oceans, and living creatures. The cosmos does not separate the microscopic from the immense. Tiny quantum interactions ripple upward into galaxies and conscious minds. A child staring at stars and a quark trapped inside a proton both belong to the same continuous structure of reality. And perhaps confinement teaches another quiet lesson as well. At the deepest level of matter, separation becomes impossible. Isolation fails. Every attempt to pull quarks apart simply creates new relationships instead. The universe responds to division by generating fresh connections. That idea sounds almost philosophical rather than physical. Yet experiments support it relentlessly. Again and again, nature rebuilds wholeness. Even destruction becomes creation. Even violent collisions inside particle accelerators produce showers of newly connected particles rather than isolated fragments. The universe seems unwilling to allow true loneliness at its foundation. And somewhere inside that refusal may hide one of the deepest truths physics has ever uncovered. Perhaps the most astonishing thing about quarks is not their confinement, nor their strange fractional charges, nor even the immense force binding them together. Perhaps the most astonishing thing is that the universe built everything familiar from entities humanity can never directly observe alone. Think about that quietly for a moment. Every mountain, every ocean wave, every human memory, every heartbeat, every star burning across the night sky, all of it emerges from quarks hidden permanently behind confinement. Reality is constructed from ingredients nature refuses to expose directly. It is almost like trying to understand a language while never seeing individual letters clearly. You only encounter entire words and sentences formed from hidden symbols beneath the surface. And somehow, from those hidden symbols, consciousness itself emerged. This raises one of the oldest philosophical questions humans have ever asked. Why does the universe possess structure at all? Why does chaos organize itself into stable patterns capable of supporting life, memory, and awareness? Physics does not fully answer that question, but quarks offer clues. The strong force creates stability through balance. Too little confinement and matter dissolves. Too much confinement and stars evolve differently. Between those extremes lies a narrow region where chemistry becomes possible. Carbon forms. Complex molecules emerge. Biology awakens. The universe walks a delicate line between chaos and order. And confinement helps maintain that balance. What makes this even stranger is that quarks themselves barely resemble ordinary objects. They possess quantum properties that defy human intuition completely. Quarks have spin, but not spin in the everyday sense of tiny balls rotating physically. Their spin is an intrinsic quantum property woven into the mathematics describing them. Quarks also obey the Pauli exclusion principle. No two identical fermions can occupy the same quantum state simultaneously. This rule governs far more than particle physics. It shapes the entire periodic table. It determines chemistry. It prevents matter from collapsing into itself. Without the exclusion principle, electrons would all fall into identical low-energy states. Atoms would lose structure entirely. Solid matter could not exist as humans know it. And quarks obey the same deep rule. Inside protons and neutrons, their quantum states arrange themselves carefully according to these invisible restrictions. The architecture of matter depends upon abstract mathematical principles operating beneath conscious experience. This realization changes how reality feels. The world appears solid and immediate to human senses. But beneath that appearance lies a hidden layer governed by symmetries, probabilities, fields, and quantum restrictions no human being evolved naturally to imagine. The universe is not built according to common sense. It is built according to mathematics. And nowhere is this more apparent than in quantum chromodynamics. The equations describing quarks and gluons are among the most successful theories in scientific history. Their predictions match experiments with extraordinary precision. Yet the behavior they predict remains deeply alien to ordinary intuition. Quarks confined forever. Forces growing stronger with distance. Vacuum fluctuations creating particles from energy. Invisible fields shaping the mass of visible worlds. Even now, physicists continue testing these ideas with increasingly sophisticated experiments. At CERN, detectors record particle collisions with astonishing detail. Vast digital systems analyze billions of events searching for tiny deviations from theoretical expectations. So far, quantum chromodynamics continues surviving every challenge. But scientists know the theory remains incomplete in one important sense. It does not easily combine with gravity. Gravity governs the large-scale structure of spacetime. Quantum chromodynamics governs the microscopic world of quarks and gluons. Yet these two frameworks remain mathematically incompatible under extreme conditions like black holes or the Big Bang itself. Somewhere deeper still, a more fundamental theory may unite them, and perhaps confinement will look different through that deeper lens. Some physicists suspect spacetime itself may emerge from quantum information and entanglement. In these ideas, geometry is not fundamental. Instead, relationships between quantum states generate the appearance of space and distance. Reality becomes a network of interconnected information rather than objects moving through pre-existing emptiness. If such theories prove correct, confinement may represent not merely a force phenomenon, but a deeper property of how information organizes itself within the universe. Again, connection appears central, not isolation. Even quantum entanglement hints toward this strange interconnectedness. Entangled particles share linked quantum states across vast distances. Measure one and the other responds instantly regardless of separation. Einstein famously disliked this implication, calling it spooky action at a distance. Yet experiments confirmed entanglement repeatedly. The universe appears fundamentally relational, and quarks may embody that principle more completely than any other known particles. There is also a strange emotional dimension to these discoveries. Human beings evolved to perceive middle-sized reality. Trees, rivers, faces, sunlight. The quantum world lies far outside natural experience. And yet, through mathematics and experimentation, fragile biological creatures living on a small planet somehow uncovered the hidden architecture of matter itself. That achievement feels almost miraculous. Tiny conscious minds assembled from confined quarks learned to investigate the confinement of quarks. The universe became aware of its own microscopic foundations through temporary patterns of organized matter called human beings. Carl Sagan once said, "We are a way for the cosmos to know itself." Quark physics gives that idea incredible depth. Every scientist studying particle collisions is ultimately made from the same confined particles they investigate. The observer and the observed arise from identical physical laws stretching back to the first moments after the Big Bang. There is no true separation between humanity and the cosmos, only different arrangements of the same underlying fields. Perhaps that is why modern physics often feels strangely spiritual despite remaining entirely scientific. The deeper reality is examined, the more interconnected everything appears. Boundaries soften, isolation dissolves, matter becomes energy, particles become fields, empty space becomes active structure, and hidden beneath all of it, quarks continue their eternal confinement. Tiny prisoners, tiny architects, tiny storms of quantum energy shaping every visible thing that has ever existed. Even now, as galaxies drift silently through darkness beyond human sight, confinement continues operating flawlessly across the universe. In distant stars, in alien worlds, in forgotten corners of cosmic voids, everywhere matter exists, quarks remain bound together through invisible gluon fields woven into spacetime itself. The universe never relaxes this rule. Not once, not anywhere, And perhaps that absolute consistency is what allows reality itself to endure across billions of years of cosmic evolution. As humanity's understanding of quarks deepened, physicists slowly realized they were confronting something more than another layer of smaller particles. Quarks were revealing a hidden philosophy embedded inside the structure of nature itself. A philosophy where stability emerges through tension, where isolation becomes impossible, where matter exists only because invisible relationships never break. And perhaps nowhere is that more dramatic than inside neutron stars. Imagine a star much larger than the Sun exhausting its nuclear fuel. For millions of years, fusion inside its core balances gravity perfectly. Outward pressure from nuclear reactions pushes against the inward crush of the star's enormous mass. But eventually the fuel runs out. Fusion slows. Gravity wins. The star collapses violently. Outer layers explode outward in a supernova bright enough to outshine entire galaxies. Meanwhile, the core implodes inward with terrifying force. Electrons and protons are crushed together into neutrons. Atomic structure itself collapses. What remains is a neutron star. A sphere perhaps 20 kilometers wide containing more mass than the sun. Matter inside becomes so dense that a single teaspoon would weigh billions of tons on Earth. Gravity near its surface distorts space-time intensely. Time itself slows slightly there compared to distant observers. And deep inside some neutron stars, pressure may become even more extreme. Neutrons themselves may begin dissolving. Confinement weakens under the crushing density. Quarks press so tightly together that boundaries between individual neutrons blur. Matter transitions into an exotic sea of deconfined quarks moving through one another inside the stellar core. A quark star may be born. If such objects truly exist, they represent one of the strangest forms of matter in the cosmos. Entire stars composed not of atoms, but of partially liberated quark matter. Ancient remnants where the universe approaches conditions last seen moments after the Big Bang. Some theories suggest these stars could contain strange quark matter rich in strange quarks alongside ordinary up and down quarks. In certain models, strange matter may actually become more stable than ordinary nuclear matter under immense pressure. That possibility leads to haunting ideas. A fragment of stable strange matter touching ordinary matter might theoretically convert nearby nuclei into additional strange matter, like a tiny seed transforming everything around it. Fortunately, evidence suggests such catastrophic scenarios are extraordinarily unlikely if possible at all. Particle collisions in nature far exceed anything humans produce in laboratories, and Earth still survives peacefully after billions of years. Still, these ideas reveal how unfamiliar matter becomes under extreme conditions. The universe contains states of reality far stranger than everyday experience suggests, and confinement sits at the center of those possibilities. Even black holes may connect indirectly to quark physics. Near the cores of collapsing stars, densities become so immense that modern theories begin breaking down. Gravity and quantum mechanics collide mathematically. Physicists still lack a complete theory unifying them fully. Some researchers speculate that confinement and spacetime geometry may share deeper relationships hidden beneath current understanding. In certain theoretical models, flux tubes between quarks resemble tiny strings vibrating through higher dimensional space. The boundaries separating particle physics and gravity begin dissolving. The universe grows increasingly interconnected the deeper science travels. And yet, despite all these cosmic implications, confinement also shapes the simplest moments of ordinary life. Every sip of water contains hydrogen nuclei stabilized by the strong force. Every breath carries oxygen atoms whose existence depends upon confined quarks formed inside ancient stars. Even the warmth of sunlight ultimately traces back to nuclear reactions governed by strong interactions deep within the sun. Human beings live immersed inside confinement constantly without ever noticing it. The force remains invisible, silent, perfectly reliable. There is something strangely comforting about that hidden stability. Beneath the chaos of history and human life, the laws governing matter continue operating with unwavering consistency. Quarks remain confined. Protons remain stable. Atoms hold together across billions of years while galaxies drift through darkness. Reality possesses deep structure beneath surface uncertainty. And perhaps that explains why the study of physics often evokes wonder beyond pure intellectual curiosity. Science does not merely provide technical knowledge. At its deepest levels, it reshapes how existence feels. When you realize most of your body's mass comes from confined gluon energy, your sense of self changes subtly. The boundary between matter and energy softens. The distinction between emptiness and substance blurs. You begin seeing ordinary reality as condensed patterns within invisible quantum fields stretching across the cosmos. Even your own consciousness arises from atoms assembled through confinement. Every thought depends upon ancient quarks forged during the cooling of the early universe. There is poetry hidden inside that fact. The same laws operating inside distant neutron stars also govern the particles inside your fingertips. The cosmos is not divided into separate worlds. The microscopic and cosmic belong to one continuous unfolding structure. And through science, the universe has slowly learned to observe itself. Tiny creatures standing on a small planet built machines capable of recreating conditions from the first moments after the Big Bang. They discovered invisible particles hidden inside matter. They uncovered forces shaping the structure of galaxies and stars. And all of it emerged from brains built from confined quarks questioning confinement itself. That recursive beauty is difficult to ignore. The universe became conscious enough to ask why quarks cannot exist alone. Perhaps future discoveries will deepen the mystery further. New accelerators may reveal unknown particles. More powerful telescopes may uncover exotic stars containing strange matter. Quantum gravity theories may finally explain why confinement emerges so naturally from mathematics. Or perhaps the deepest truths will remain partially hidden forever. Science advances endlessly, but each answer reveals new questions waiting beneath it. Every layer of understanding opens another layer below. Atoms gave way to nuclei. Nuclei gave way to quarks. And somewhere beyond quarks may lie structures humanity has not yet imagined. But even if deeper layers exist, one fact remains extraordinary. The visible universe depends entirely upon confinement. Without it, there would be no atoms, no chemistry, no stars burning through cosmic night, no planets orbiting quietly beneath ancient skies, no living creatures wondering about existence. The universe built everything familiar from particles it refuses to let stand alone. And perhaps that hidden rule carries a quiet message. At the deepest level of reality, existence itself may not emerge from isolation, but from connection held together across the darkness by invisible forces older than stars. If you could somehow shrink yourself smaller than an atom, smaller than a proton, smaller than even the quarks hidden inside it, the familiar universe would disappear completely. There would be no solid surfaces, no colors, no sounds, no ordinary sense of space. Instead, you would enter a realm governed by probability, quantum fields, and invisible forces vibrating beneath reality like hidden currents beneath a calm ocean. And within that strange realm, confinement would still dominate everything. The farther you traveled into the microscopic world, the more impossible isolation would become. This idea clashes deeply with human instinct because human beings experience life through separation. We perceive ourselves as distinct individuals moving through an external world. Objects appear independent. Trees stand apart from rivers. Mountains seem separate from stars. Even our own bodies feel isolated from the surrounding universe. But quarks tell a different story. At the deepest known layer of matter, nothing remains fully independent. Every quark exists only through interaction. Every proton emerges from dynamic relationships between quarks and gluons. Even the vacuum surrounding them participates continuously through quantum fluctuations. Reality behaves less like disconnected objects and more like an endless web of interactions. Modern physics repeatedly returns to this theme. Electromagnetism links charged particles across space. Gravity curves spacetime itself around mass and energy. Quantum entanglement connects particles through invisible correlations. And confinement prevents quarks from existing alone entirely. Connection is not a side effect of reality. It may be the foundation of reality. This perspective becomes even stranger when physicists consider empty space itself. According to quantum field theory, every region of space contains underlying fields extending across the entire universe. Electrons are excitations of the electron field. Quarks are excitations of quark fields. Photons emerge from the electromagnetic field. Particles are not isolated little beads floating through emptiness. They are localized vibrations within continuous cosmic fields. Imagine the surface of a vast ocean. Individual waves appear separate for a moment, but every wave belongs to the same underlying water. Similarly, particles may be temporary patterns rising within deeper quantum structures stretching across spacetime itself. And confinement governs how certain patterns can emerge. A lone electron may travel freely because electromagnetism weakens with distance. But quark fields interact through gluons carrying color charge themselves. The mathematics traps quarks into collective states. Nature permits only color-neutral combinations to survive across large distances. The universe imposes hidden rules upon existence. And remarkably, those rules create stability. Without confinement, stars would not burn the way they do. Heavy elements would not form properly. Carbon chemistry might never emerge. The atoms making up DNA, proteins, oceans, and human brains would vanish into a radically different universe where complexity perhaps could not survive. Confinement is not merely a prison. It is an engine of creation. This becomes beautifully clear when considering stellar evolution. Inside stars, nuclear fusion transforms hydrogen into helium and eventually into heavier elements. These reactions depend entirely upon stable protons and neutrons. Confinement holds those particles together despite the intense heat and pressure inside stellar cores. Every atom of oxygen you breathe was forged inside stars stabilized by confinement. Every atom of iron inside your blood once formed during ancient stellar explosions where strong interactions shaped nuclear reactions across collapsing suns. In a very literal sense, confinement connects your existence directly to the life cycles of stars. Carl Sagan famously said humans are made of star stuff. Quark physics deepens that truth. Humans are made of confined star stuff, organized energy locked into stable matter through invisible gluon fields born from the cooling of the early universe. There is something profoundly calming about that realization. The particles inside your body have traveled through cosmic history itself. Some quarks within you may once have existed inside ancient stars that died billions of years before Earth formed. Matter recycles endlessly across cosmic time. Atoms drift between galaxies, stars, planets, oceans, and living creatures. And through every transformation, confinement remains constant. The same strong force operating inside the first protons after the Big Bang still operates inside your fingertips tonight. Physics often sounds cold from a distance because it speaks through mathematics and experiments. But beneath the equations lies an extraordinary narrative. A universe beginning as pure energy cools into quark-gluon plasma. Confinement locks quarks into hadrons. Atoms emerge. Stars ignite. Galaxies spin through darkness. Life awakens. Conscious beings begin asking questions about the hidden structure beneath matter. The cosmos evolves towards self-awareness. And somehow, the same laws shaping neutron stars and particle collisions also shape human curiosity itself. Even now, beneath laboratories deep underground, enormous detectors continue listening for whispers from the quantum world. Scientists search for deviations from known physics, tiny anomalies, unexpected particles, cracks in current theories hinting toward deeper truths hidden beyond the standard model. Because despite all humanity has discovered, enormous mysteries remain. Why do quarks possess the masses they do? Why are there exactly 6 flavors? Why does confinement emerge so absolutely? How does quantum chromodynamics connect ultimately to gravity? Why does the universe possess laws capable of generating complexity and consciousness at all? These questions linger quietly at the edge of modern physics, and perhaps they always will. The universe may never surrender every secret completely. Each discovery seems to reveal deeper layers beneath it. Science is not a staircase with a final step. It may be an endless descent into increasingly subtle patterns hidden beneath existence. Yet even partial understanding changes how reality feels. Once you realize most visible mass comes from confined energy rather than particles themselves, ordinary objects begin appearing differently. A stone becomes organized quantum motion. A human body becomes ancient stellar matter held together through invisible forces. Even emptiness becomes alive with fluctuating fields and virtual particles. The universe transforms from a collection of objects into a living structure of relationships. And at the heart of that structure, quarks remain forever bound together in silence. Tiny prisoners shaping worlds. Tiny fragments of the early cosmos still carrying the memory of the Big Bang inside every atom surrounding you now. There is a quiet irony hidden inside the story of quarks. Human beings spent thousands of years believing the visible world was fundamental. Mountains felt solid. Stone felt permanent. Matter appeared simple and direct. Yet the deeper science descended, the more reality dissolved into abstractions invisible to ordinary senses. First came atoms hidden beneath matter, then nuclei hidden inside atoms, then protons and neutrons hidden inside nuclei, then quarks hidden inside protons. And beneath quarks may still wait deeper layers humanity has not yet imagined. The universe keeps retreating from certainty. But perhaps what makes quarks especially haunting is that they blur the distinction between existence and impossibility. Physicists can calculate their properties with astonishing precision. Experiments confirm their behavior constantly. Yet no one will ever place a single quark into a bottle or watch one drift freely across space. Confinement prevents that forever. The universe permits quarks to exist only as members of larger structures. Their individuality can never fully separate from relationship. This idea feels strangely opposite to how humans often imagine reality. We tend to think fundamental things should be independent, self-contained, simple. Yet the deeper physics travels, the more interdependence dominates everything. Even space-time itself may not be fundamental. Some modern theories suggest space emerges from quantum entanglement. Distance may arise from informational relationships rather than existing independently. Geometry itself could be a consequence of deeper quantum structures connecting particles across the cosmos. If true, then the universe is even stranger than it already appears. Reality would not be built from objects sitting inside space. Instead, space itself would emerge from relationships between underlying quantum states. And once again, connection would stand beneath separation. This theme repeats so often in modern physics that it becomes difficult to ignore. Quantum entanglement links distant particles. Gravity binds stars into galaxies. Electromagnetism shapes chemistry and biology. Confinement locks quarks into stable matter. At every scale, existence emerges through interaction. Nothing survives entirely alone. Even black holes, once thought to erase information completely, now appear deeply connected to quantum mechanics through holographic principles and entropy relationships. The boundaries between matter, information, and geometry continue dissolving under scientific investigation. The universe grows less mechanical and more interconnected the deeper we look. And strangely, this interconnectedness extends across time as well. Every atom inside your body carries a history older than Earth itself. Hydrogen nuclei formed shortly after the Big Bang. Carbon emerged inside ancient stars. Heavier elements formed during stellar explosions scattering matter across galaxies. Eventually, clouds of gas and dust collapsed into the sun and planets. Chemistry organized itself into biology. Biology evolved consciousness. You are part of an unbroken chain stretching back nearly 14 billion years. And beneath every stage of that chain lies confinement. Without the strong force trapping quarks together, cosmic history would collapse before stars even formed. The universe would remain a thin sea of radiation and unstable particles drifting endlessly through darkness. Confinement allowed complexity to exist. In a sense, every memory you possess depends upon quarks refusing isolation. Even your thoughts emerge from electrical signals moving through neurons built from atoms stabilized by the strong force. Consciousness itself rides atop layers of confinement extending downward into quantum fields hidden beneath matter. There is something almost impossible about that realization. Tiny confined particles inside ancient stars eventually became living creatures capable of contemplating confinement itself. The universe folded back upon itself into awareness. And still, despite all humanity has uncovered, confinement remains partly mysterious mathematically. Physicists know quantum chromodynamics predicts it. Simulations reproduce it. Experiments confirm it relentlessly. Yet deriving confinement rigorously from first principles remains one of the great unsolved challenges in theoretical physics. In fact, the Clay Mathematics Institute listed proving the existence of Yang-Mills theory and explaining confinement as one of the Millennium Prize problems. The reward for solving it stands at $1 million. Even now, some of humanity's greatest minds continue wrestling with the mathematics hidden beneath quark confinement. That unfinished mystery matters because it reminds us science remains alive. Physics is not complete. There is no final textbook explaining every layer of reality. The universe still contains unanswered questions waiting silently beneath current understanding. And perhaps it always will. There may never be a final bottom layer where curiosity ends forever. Each generation descends deeper into nature only to discover new mysteries beneath old answers. The Greeks imagined indivisible atoms. Modern science discovered quarks. Future civilizations may discover structures hidden beneath quarks themselves. Or perhaps they will uncover entirely new ways of understanding reality beyond particles altogether. The future remains open, yet even if deeper layers exist, confinement already teaches something profound about existence. It reveals that matter is not static substance but organized energy shaped through invisible relationships. The solidity of everyday life emerges from dynamic quantum interactions beneath perception. A table feels solid because of electromagnetic repulsion between atoms. Those atoms remain stable because electrons obey quantum rules. Nuclei survive because confinement binds quarks together through gluon fields. And those gluon fields emerge from symmetries hidden within the fabric of reality itself. The ordinary world rests atop astonishing depths. Perhaps that is why looking at the night sky can feel strangely emotional once you understand modern physics. The stars no longer appear as distant lights alone. They become enormous furnaces transforming confined quarks into heavier elements through nuclear fusion. They become engines of cosmic evolution creating the ingredients for planets and life. The universe feels alive with hidden processes unfolding silently beneath appearances. And somewhere inside every star, every planet, every living creature, quarks continue their endless dance, exchanging gluons, shifting color charge, remaining forever bound inside protons and neutrons that quietly hold the visible cosmos together. The confinement never stops. Even now, while galaxies drift through darkness billions of light years away, invisible flux tubes continue binding quarks together across the universe. Tiny storms of energy flicker endlessly inside every atom surrounding you. And perhaps the most beautiful part of all this is that the cosmos did not need to produce conscious observers capable of discovering these truths. Yet somehow it did. From confined energy emerged minds able to wonder why confinement exists at all. Perhaps one day, far in the future, humanity will build machines capable of probing reality far beyond anything possible today. Particle accelerators may circle entire planets. Quantum detectors may drift silently through deep space. Artificial intelligences may analyze physical laws with levels of precision no human mind can achieve alone. And still, even those future civilizations may remain haunted by the same mystery. Why does the universe exist in this particular form? Why these laws? Why these particles? Why confinement? Because beneath every equation in physics lies an uncomfortable truth. Science can describe how reality behaves with extraordinary accuracy, but the ultimate reason those laws exist at all remains hidden. Quantum chromodynamics explains the behavior of quarks and gluons beautifully. Yet it does not explain why the universe possesses color-charge symmetry in the first place. It describes confinement, but not why reality chose a structure where confinement emerges naturally. The deeper we descend into physics, the more existence begins to resemble an intricate pattern without visible origin. Some physicists believe a final unified theory may eventually explain everything. A single mathematical framework uniting gravity, quantum mechanics, space-time, particles, and forces into one elegant structure. Others suspect no final theory exists at all. Perhaps reality is endless, layer beneath layer beneath layer forever. If that is true, then humanity's search for understanding may never truly end. And perhaps that endlessness is beautiful, because curiosity itself becomes part of the universe's unfolding story. For thousands of years, humans looked upward at the stars with no idea what they truly were. Ancient civilizations imagined gods, spirits, fires carried across the heavens. They could not know that every star was powered by nuclear fusion governed partly by confinement deep inside atomic nuclei. They could not know their own bodies were assembled from ancient stellar matter stabilized by invisible quark interactions. And yet they still wondered. That impulse to question reality may be one of the most extraordinary things the cosmos has ever produced. Tiny temporary beings standing on the surface of a small planet somehow learned to uncover the hidden structure of matter itself. From stone tools to particle colliders, from myths to quantum field theory, the journey feels almost impossible when viewed across the span of history. And still the universe remains larger and stranger than human understanding. Even now, dark matter surrounds galaxies invisibly. Dark energy accelerates cosmic expansion for reasons still unknown. Black holes challenge the boundaries of quantum theory and gravity. The earliest moments of the Big Bang remain partially hidden behind mathematical uncertainty. Reality continues receding beyond complete comprehension. But perhaps quarks offer a subtle lesson about that mystery. Human intuition expects truth to become simpler as we descend toward fundamental layers. We imagine peeling reality like an onion until finally reaching a small solid core explaining everything else. Instead, the opposite happened. The deeper science traveled, the more relational and interconnected existence became. Quarks cannot exist alone. Fields overlap across space. Vacuum fluctuations create particles. Geometry may emerge from quantum information itself. Reality did not simplify into isolated building blocks. It transformed into networks of interaction. And maybe consciousness itself follows the same pattern. Human minds do not emerge from single neurons acting independently. consciousness arises from vast patterns of communication within the brain. Relationships generate awareness just as quark interactions generate matter. At every scale, complexity emerges through connection. The universe seems to build upward through cooperation between smaller processes rather than isolated independence. Even galaxies form this way. Gravity gathers stars into spirals and clusters. Stars forge heavy elements. Supernovae scatter those elements outward. New stars and planets emerge from the debris. Life evolves from chemistry. Consciousness arises from biology. Everything depends upon everything else. And beneath all of it, confinement quietly continues binding quarks together inside matter itself. There is something deeply calming about that continuity. The same laws operating inside distant galaxies also operate inside your own body tonight. The same confinement mechanism stabilizing neutron stars stabilizes the atoms in your fingertips. You belong fully to the cosmos, not metaphorically, physically. Every particle within you participates in processes billions of years old. Every proton inside your body formed from quarks confined shortly after the Big Bang. Those protons survived through stellar explosions, interstellar clouds, planetary formation, biological evolution, and human history to exist inside you now. Matter remembers the universe. And perhaps this is why modern cosmology often evokes a strange emotional response beyond scientific fascination. The story physics reveals is not merely technical. It is existential. It changes how humans understand themselves within reality. You are not separate from the universe observing it from outside. You are one temporary arrangement of the universe observing itself from within. A pattern of confined energy becoming aware for a brief moment before dissolving back into cosmic history. That realization can feel overwhelming at first. Yet it can also feel peaceful. Human life becomes connected to something vastly larger than individual experience. Every breath joins a process billions of years in motion. And somewhere beneath all human concerns, quarks continue their invisible dance uninterrupted. Even while civilizations rise and fall, even while stars are born and die, even while galaxies drift slowly apart through expanding spacetime, confinement endures. Tiny gluon fields continue binding quarks together inside every atom across the observable universe. The force never sleeps, never weakens, never forgets its role in shaping reality. Perhaps one day humanity will finally uncover a deeper explanation for why confinement exists. Perhaps future theories will reveal hidden geometries or quantum principles beneath the strong force itself. Or perhaps confinement will remain partly mysterious forever. A reminder that reality always contains depths beyond complete understanding. Either way, the existence of quarks already reveals something extraordinary. The visible universe is not built from isolated things. It is built from relationships so strong that reality itself refuses to let them break apart. And now, as our journey slowly comes to an end, return for a moment to the simple mystery that began tonight. What is a quark? At first, the answer seems straightforward. A quark is a fundamental particle, one of the tiny building blocks hidden inside protons and neutrons, a carrier of fractional electric charge, a participant in the strong nuclear force. But by now, the question feels deeper than that. A quark is also a reminder that reality is stranger than human intuition was ever designed to understand. It is a particle that can never stand alone, a fragment of matter permanently bound by invisible fields, a tiny quantum excitation trapped inside relationships so powerful that the universe itself refuses to let them break. For thousands of years, humanity imagined the universe as solid and certain. Ancient people looked at stone and believed permanence lived there. They looked at stars and imagined eternal fires hanging in perfect heavens. Yet beneath all appearances, reality was far more delicate and astonishing than anyone suspected. Matter is mostly empty space. Mass emerges largely from confined energy. Particles behave like waves and probabilities. Vacuum itself seethes with hidden activity. And at the deepest known layer of ordinary matter, quarks remain forever confined together in darkness. There is something almost poetic about that hidden imprisonment. The visible world depends entirely upon relationships that can never fully separate. The universe builds stability not through isolation, but through connection held together across unimaginable scales. Without confinement, atoms would vanish. Without atoms, chemistry would vanish. Without chemistry, stars, planets, oceans, forests, and living minds would never appear. The cosmos as humans know it exists because quarks cannot escape one another. And perhaps there is comfort hidden inside that idea. Every atom in your body tonight was shaped by the same laws governing the earliest moments after the Big Bang. The protons inside your bloodstream contain quarks confined nearly 14 billion years ago during the cooling of the young universe. Those particles survive through cosmic expansion, stellar birth, stellar death, planetary formation, biological evolution, and countless generations of human history. Now they exist quietly within you, tiny ancient structures older than Earth itself. Even now, while you rest beneath the night sky, confinement continues everywhere across the universe. Inside distant galaxies billions of light years away, inside collapsing neutron stars hidden within dark regions of space, inside grains of dust drifting between stars, inside every living creature breathing softly on Earth tonight. The same invisible gluon fields continue binding quarks together without pause. The force never tires, never weakens, never forgets. And although humans may never hold a lone quark in their hands, perhaps that limitation carries its own kind of beauty. Science often advances by breaking things apart and isolating smaller pieces. But quarks resist that approach completely. They teach us that some parts of reality exist only through relationship. Their identity cannot survive separation. The deeper physics travels, the more this lesson repeats itself. Particles connect through fields. Matter connects through forces. Galaxies connect through gravity. Life connects through chemistry and evolution. Consciousness connects through networks of neurons and memory. Again and again, reality reveals itself not as isolated objects drifting through emptiness, but as patterns woven together within a larger whole. And maybe that is the quiet truth hidden beneath confinement. The universe does not seem designed for loneliness. Even at the smallest scales, existence emerges through interaction, through balance, through invisible bonds holding structures together across darkness and time. Perhaps that is why the night sky can feel both immense and strangely intimate at the same moment. The stars overhead are unimaginably distant, yet the particles inside them obey the same laws shaping your own existence. The cosmos is vast beyond comprehension, yet its deepest structures remain shared everywhere. You are not separate from the universe observing it. You are one brief expression of it, a temporary arrangement of ancient confined energy becoming aware beneath the stars. And one day, far in the future, the atoms making up your body will scatter again into the cosmos. They will drift through oceans, soil, atmosphere, perhaps even interstellar clouds long after human history has faded. But the quarks within those atoms may continue enduring almost unchanged across spans of time difficult to imagine. Tiny confined remnants of the early universe traveling endlessly through cosmic history. There is something peaceful about that continuity. The universe changes constantly. Stars ignite and collapse. Galaxies collide. Species appear and vanish. Civilizations rise and disappear into memory. Yet beneath all transformation, the hidden architecture of matter persists quietly. Quarks continue dancing inside protons. Gluons continue binding them together. Reality continues unfolding through invisible relationships hidden beneath ordinary perception. And perhaps tonight, as you grow sleepy and the world around you softens into silence, you can carry one final thought gently into the darkness. Everything you have ever touched, everything you have ever loved, every mountain, ocean, cloud, tree, memory, and living heartbeat, all of it was built from tiny particles the universe refuses to let stand alone. Perhaps one day, far in the future, humanity will build machines capable of probing reality far beyond anything possible today. Particle accelerators may circle entire planets. Quantum detectors may drift silently through deep space. Artificial intelligences may analyze physical laws with levels of precision no human mind can achieve alone. And still, even those future civilizations may remain haunted by the same mystery. Why does the universe exist in this particular form? Why these laws? Why these particles? Why confinement? Because beneath every equation in physics lies an uncomfortable truth. Science can describe how reality behaves with extraordinary accuracy, but the ultimate reason those laws exist at all remains hidden. Quantum chromodynamics explains the behavior of quarks and gluons beautifully. Yet it does not explain why the universe possesses color-charge symmetry in the first place. It describes confinement, but not why reality chose a structure where confinement emerges naturally. The deeper we descend into physics, the more existence begins to resemble an intricate pattern without visible origin. Some physicists believe a final unified theory may eventually explain everything. A single mathematical framework uniting gravity, quantum mechanics, space-time, particles, and forces into one elegant structure. Others suspect no final theory exists at all. Perhaps reality is endless, layer beneath layer forever. If that is true, then humanity's search for understanding may never truly end. And perhaps that endlessness is beautiful, because curiosity itself becomes part of the universe's unfolding story. For thousands of years, humans looked upward at the stars with no idea what they truly were. Ancient civilizations imagined gods, spirits, fires carried across the heavens. They could not know that every star was powered by nuclear fusion governed partly by confinement deep inside atomic nuclei. They could not know their own bodies were assembled from ancient stellar matter stabilized by invisible quark interactions. And yet they still wondered. That impulse to question reality may be one of the most extraordinary things the cosmos has ever produced. Tiny temporary beings standing on the surface of a small planet somehow learned to uncover the hidden structure of matter itself. From stone tools to particle colliders, from myths to quantum field theory, the journey feels almost impossible when viewed across the span of history. And still the universe remains larger and stranger than human understanding. Even now, dark matter surrounds galaxies invisibly. Dark energy accelerates cosmic expansion for reasons still unknown. Black holes challenge the boundaries of quantum theory and gravity. The earliest moments of the Big Bang remain partially hidden behind mathematical uncertainty. Reality continues receding beyond complete comprehension. But perhaps quarks offer a subtle lesson about that mystery. Human intuition expects truth to become simpler as we descend toward fundamental layers. We imagine peeling reality like an onion until finally reaching a small solid core explaining everything else. Instead, the opposite happened. The deeper science traveled, the more relational and interconnected existence became. Quarks cannot exist alone. Fields overlap across space. Vacuum fluctuations create particles. Geometry may emerge from quantum information itself. Reality did not simplify into isolated building blocks. It transformed into networks of interaction. And maybe consciousness itself follows the same pattern. Human minds do not emerge from single neurons acting independently. Consciousness arises from vast patterns of communication within the brain. Relationships generate awareness just as quark interactions generate matter. At every scale, complexity emerges through connection. The universe seems to build upward through cooperation between smaller processes rather than isolated independence. Even galaxies form this way. Gravity gathers stars into spirals and clusters. Stars forge heavy elements. Supernovae scatter those elements outward. New stars and planets emerge from the debris. Life evolves from chemistry. Consciousness arises from biology. Everything depends upon everything else. And beneath all of it, confinement quietly continues binding quarks together inside matter itself. There is something deeply calming about that continuity. The same laws operating inside distant galaxies also operate inside your own body tonight.